9th Standard ICSE Chemistry Chapter 6 Hydrogen. Anita Prasad textbook. Hydrogen was the first element to be formed after the universe was formed, millions of years ago. More precisely, the Big Bang happened 13.8 billion years ago. Hydrogen is the lightest and the simplest atom known to humans. It just has one proton and one electron. It is colorless, odorless, and tasteless. Air is 14 times denser than hydrogen. Hydrogen is the element that makes the sun shine. In fact, in all the stars, it's the hydrogen which undergoes nuclear fusion to form helium and heavier elements. And that's what gives all the light and heat. Discovery of hydrogen, marketers read. Robert Boyle was the first scientist who was able to collect it. But the name hydrogen was coined by Antoine Lavoisier. Occurrence. It is the 9th most abundant element in the Earth's crust, not in the free state, in the combined state in the form of compounds. In the free state, it is available in the atmosphere, but very rarely will you find hydrogen. It's in traces. But it's abundant in the stars and the nebulae where stars are born. This is not Mickey Mouse, it's a molecule of water. You can see two single covalent bonds. But it's a polar covalent bond, meaning the shared pair of electrons are not equally distributed. It is closer to the oxygen, giving it a slight negative charge, and far away from the hydrogen, giving it a slight positive charge. And water molecules are attracted to each other by intermolecular forces of attraction called van der Waals forces. That's why water has a curiously high boiling point. Otherwise, covalent substances are supposed to have low boiling point. Hydrogen is present everywhere, every organic compound, fats, carbohydrates, proteins, your skin, your tissues, your cells, your cytoplasm, everything has hydrogen. Hydrogen is very important. It's quite combustible, it's inflammable, and it's a reducing agent. It is used to make fuels. More about it later. Its atomic weight is 1.008, more accurately, but we just considered it to be 1 because it has one nucleon. Since its electronic configuration is just 1, it has valency 1, so it is placed in group 1, although it's not an alkali metal. And since it has only one shell, it is in period number 1, because the period number tells us the number of shells in an atom. It also shows properties of halogens, so sometimes it is placed in group 17 as well. So hydrogen has a dual nature. There are 5 properties of hydrogen which are similar to that of those of alkali metals. Although hydrogen is not considered to be a metal, it's a non-metal. But it does have some alkali metal properties, like it has one valence electron, just like sodium, lithium, potassium. It can lose electrons to form cations, just like the alkali metals. Mark this as a good reason. Reactions of hydrogen are called protonic. When it loses electrons, it becomes just a naked proton, H+. Like alkali metals, even hydrogen has affinity for, attraction for non-metals. It can, just like sodium oxide is formed. Similarly, we have hydrogen oxide, which is water, hydrogen sulfide, hydrogen chloride. The only difference is that this is a basic oxide and this is a neutral oxide. And this is acidic. Hydrogen can act as a reducing agent. In this equation, notice that copper oxide has been reduced to copper. Losing oxygen is called reduction. Gaining oxygen is called oxidation. Perhaps we got this copper oxide while mining it, and we want pure copper. So in the process of metallurgy, we use some reducing agents like metals, carbon monoxide, and even hydrogen, because these reducing agents steal away the oxygen and pure metal is left behind. Now there are 4 ways in which hydrogen is similar to halogens. First of all, it can accept an electron sometimes to become an anion, just like halogens do. Also, its atomicity, it's 2. It's diatomic, just like halogens. Alkali metals are monoatomic. Halogens are typically gaseous nonmetals. Even hydrogen is gaseous nonmetal. Fluorine, chlorine are gaseous. Bromine is liquid, which can vaporize very easily. And iodine is a solid, but it's sublimatory, so it also vaporizes very easily. One thing about hydrogen which sets it apart from all other elements is that it has only one shell, unlike the alkali metals and the halogens. Only helium is the other atom which has only one shell. Now, preparation of hydrogen. The general methods include action of water on metals, or action of acids on metals, or action of alkalis on metals. Then we will also study the lab method and the industrial method. First, we should understand the activity series of metals. It is arranged in the decreasing order of reactivity. किटकैट नहीं, कैडबरी मांगो, अलादीन, जिंदगी फिर भी प्रॉब्लमेटिक है, कोलगेट हटाओ और अपनाओ पेप्सोडेंट. But gold and platinum is missing in this activity series because they will not react at all with acid or alkali or with water. In fact, even the elements below hydrogen are inactive, so they will not react easily with these substances. So our focus should be on the metals above hydrogen in the activity series, potassium being the most reactive. So this is a definition of activity series. Remembering this helps us to decide which metal can displace which one in a reaction. So hydrogen can be easily replaced or displaced by any of the other metals on top, giving pure hydrogen gas. Let's talk about producing hydrogen from water. Potassium, sodium and calcium are quite reactive metals, so they will react even with cold water, whereas the next few elements, they will not react with cold water because they are less reactive, so we will need boiling water or rather steam to produce hydrogen. When you drop potassium in water, it's so exothermic that the hydrogen produced catches fire and you see a lilac flame because some vapors of potassium are also present in that flame. And it floats, this potassium piece floats as the reaction takes place and it darts about. Even sodium globule darts about on the surface, but this time it gives golden yellow flame. Even this is exothermic, but less exothermic compared to this. Calcium reacting with water to give hydrogen gas is also exothermic, but not so hot that there will be a flame involved. Also, calcium is quite dense, so it will settle at the bottom, and calcium hydroxide is formed, which is partially soluble in water, so it will turn the solution milky. So in all these three cases, alkalis are produced. Litmus will turn red. The hydrogen thus produced can be collected by downward displacement of water. The water level will fall down as hydrogen is collected on top. We use this method because hydrogen is hardly soluble in water and it is highly combustible, so we should not collect it in the presence of air, because when hydrogen mixes with air, it forms a detonating mixture. It doesn't explode immediately, sparks are also required, but it's quite risky. The next few metals cannot react with cold water. They can react only with steam. And they will not give hydroxides, they would rather give oxides. Magnesium, zinc, iron. In fact, this reaction is quite unstable, it's reversible. So the triferric tetroxide which is formed can give you back the reactants. Magnesium can react with boiling water to give magnesium hydroxide, but with steam it gives magnesium oxide. Mark this as a give reason. It says that if you're using this reaction to produce hydrogen, make sure that you remove the hydrogen quickly from that container, because if it stays in contact with this, it will lose the hydrogen, you will get back your steam. As you can see, the reversible reaction happening. Lead is not used because it is not very reactive. Very high temperature will be required for the reaction to take place. It's not worth it. Also, it's usually covered with a coating which stops the reaction. Next, what if you want to use acids? Potassium, sodium is ruled out for lab processes because the moment you drop an acid on them, the reaction is quite violent. You will get hydrogen, but it's very risky. Calcium is expensive, calcium, magnesium. So iron, so zinc is the best bet to produce hydrogen in the lab settings. Iron can also be used, but again, it has some impurities practically. And copper, lead, and mercury won't react. Lead hardly reacts. It requires a very high temperature, and there are impurities in lead in the coating. When the reactions are taking place, make sure we use dilute HCl or dilute H2SO4. You can't use nitric acid, because if you use dilute nitric acid, it's a oxidizing agent. Instead of giving you hydrogen, it will give you water plus NO gas. And even if you use conc nitric acid, it won't work. Even that is an oxidizing agent. So it will oxidize the hydrogen into water and give you NO2 gas, a reddish brown gas. The only way to get hydrogen using nitric acid is using very dilute 1% concentration nitric acid. This will reduce its oxidizing property and it will start behaving like a typical acid and give you the required hydrogen. But this will work only with magnesium and manganese at a very low temperature. The next way to get hydrogen is by using alkalis. Now, usually metals don't react with alkalis, but there are three special metals which are amphoteric metals. They don't just react with acids, as we saw earlier, they can also react with alkalis, but hot and conc alkali, to give salt and hydrogen gas. The aluminum reaction was interesting. It required water as well. This reaction is not very important, mark it as read. Now in the lab, which method is used? As I had told you earlier, the zinc with acid method is used. We have this round bottom flask with zinc granules. Zinc granules are commercially available. They have some impurities like copper which act like a catalyst, hence we should use them. Mark it as a GR. When we are pouring acid into this flask, we will use a thistle funnel. Make sure the tip of the funnel is submerged in this solution so that the hydrogen produced doesn't escape via it, but rather it is collected into this beaker and delivered via the delivery tube. And it is collected by downward displacement of water for reasons I had explained earlier. So mark this as a GR as well. However, along with hydrogen, some moisture may also be collected, so we'll have to use a drying agent later on to absorb all the moisture, a drying agent like fused calcium chloride or phosphorus pentoxide, something which doesn't react with hydrogen. Why do we use zinc? Why not sodium, calcium, potassium? They are quite very highly reactive. Calcium, magnesium are expensive. Aluminum forms a protective coating around it which will stop the reaction. Iron requires heating and it has impurities. Lead, again, it forms insoluble coatings around it. For example, lead plus HCl forms lead chloride, or lead plus H2SO4 forms lead sulfate. Both are insoluble salts. They'll form a coating and the reaction will stop. So mark these as GRs. And make sure you use dilute acids, because conc sulfuric acid will again act like an oxidizing agent and oxidize the hydrogen into water. We don't want water, we want hydrogen, and even SO2 gas is released. But when we use granulated zinc, some impurities are present, so some other gases are also produced in small quantities. So if you want pure hydrogen, we'll have to get rid of all those gases using some washer bottles. It looks something like this. Each chemical absorbs some gases so that in the end we get pure hydrogen. So arsine and phosphine are removed by silver nitrate. SO2, CO2, NO2 are removed by conc KOH, caustic potash. H2S is removed by using lead nitrate. Nitrogen gas can be removed by using a palladium foil. And moisture, of course, by fused calcium chloride. Test for hydrogen. Well, it burns quietly with a blue flame if it's pure hydrogen, but usually in the lab settings, it comes in contact with air, so we will hear a pop sound, proving that it's hydrogen gas. Some precautions during the lab preparation. Make sure the apparatus is airtight because hydrogen is combustible. If there is a leakage, it's quite risky. And if it comes, keep flames away. Just in case if there is a leakage, then it will lead to an explosion. Second GR, start collecting hydrogen after some time. Let the air inside escape out and then collect it over water. Because if there is air along with hydrogen, it forms a detonating mixture. Mention that. Third GR I've already explained. That was lab preparation on a small scale. But what if you want to prepare hydrogen on a large scale, industrial preparation? We use a Bosch process. It has two steps. Step number one, we heat hot coke, that is carbon, with steam at 1000 degrees Celsius to form water gas, a combination of two gases. It's a mixture. So we got hydrogen, but it doesn't stop here. This water gas will further react with excess of steam at 450 degrees Celsius to give carbon dioxide and even more hydrogen. So ultimately we have a mixture of three gases: hydrogen, carbon monoxide and carbon dioxide. Not all the carbon monoxide is converted to carbon dioxide. The second step will require the use of catalyst and promoter. But now I want pure hydrogen, so I'll have to get rid of the carbon monoxide and carbon dioxide. So for that, I will pass the mixture through a KOH solution, because KOH will remove the carbon dioxide at least. And carbon monoxide can be removed by passing the mixture through ammoniacal cuprous chloride, which will absorb the carbon monoxide. So only hydrogen will be left. But how do I collect it? Now again, if I collect it over water, there'll be some moisture in it. So this time, let's collect it over mercury. Another method of producing hydrogen on a large scale is by electrolysis of acidulated water. We pass electricity through acidified water. Pure water is not a conductor of electricity, it doesn't have free ions. But if you add a few drops of dilute sulfuric acid, water will ionize to give you some hydronium ions and hydroxyl ions, and then electricity can pass through it to get oxygen at the anode, vowels, and hydrogen at the cathode. So this is beneficial because not only are we getting hydrogen but even oxygen. This apparatus is called Hoffman voltameter, not voltmeter, that is in physics for measuring potential difference. Also notice that After a long time, we will see that the volume of hydrogen gas is double that of oxygen gas collected, because after all, water has a H2O, hydrogen and oxygen ratio is 2:1. And this hydrogen is 99.9% pure, no impurities. So that's another advantage of this method. Mark this as a give reason. Some physical properties, nature, learn it. Solubility, it's practically insoluble, but the values are just marked as read. Even these values are read. Conductivity, it is the best conductor of heat among gases, but nothing compared to a metal. Density values are, well, just read it. Mark this as a give reason. Earlier, hydrogen was used to make meteorological balloons. It is the lightest gas, but because of its inflammable nature, now we use helium balloons because helium is also light enough. Mark this as a give reason as well, and even this one. Hydrogen balloons rise up, proving that they are less dense compared to air. But after some time, the balloon will sink because the hydrogen will diffuse out of the plastic balloon, and air might also seep in. And this ability of the hydrogen to diffuse out rapidly through porous spots or balloons is a simple way to separate hydrogen from a mixture of gases. Another property shown by hydrogen is occlusion, or also called adsorption of gases on a surface. Mark this as a definition. Absorption means something seeping into something else. For example, a sponge absorbs water, the water seeps into the pores of the sponge. But adsorption is a surface phenomenon. Here, the hydrogen gas won't go into the palladium or platinum or nickel or gold. It would just get stuck on the surface of the metal. So, this is useful in reactions such as hydrogenation reactions, in which unsaturated compounds like oils, they become saturated by adding hydrogen to them chemically. And then that's how ghee is produced, vanaspati ghee. Now, chemical properties of hydrogen. Hydrogen is a neutral gas and it doesn't affect litmus. Combustibility, it's a combustible gas, but it doesn't support combustion. So we need oxygen or some other support of combustion. Only in the presence of that will hydrogen burn. And when hydrogen burns, water is produced, as you can see in this experiment. But how can we prove that the condensed steam is water? The test for water is it turns anhydrous white copper sulfate blue, or it turns blue cobalt chloride paper pink. Hydrogen reacts with chlorine as well to form hydrogen chloride gas. Mention gas, because if you don't mention that or don't put an up arrow, it seems it is hydrochloric acid, which is formed by dissolving HCl gas in water. This should be done in the presence of diffused sunlight, not direct sunlight, because then it will be explosive, and without sunlight it won't happen unless some other catalyst is used. Mark this as a GR. Next, reaction with nitrogen. This is called Haber's process, where two gases combine reversibly to give a third gas. Certain conditions are required: temperature, pressure, catalyst, and even a promoter can be used, molybdenum. Reaction with sulfur, hydrogen sulfide, rotten egg smell, turns moist lead acetate paper silvery black or black. Hydrogen reacts with metals to form hydrides. They are ionic compounds, and when these hydrides are dissolved in water, we get alkalis. These are hydrogenation reactions, addition reactions, where unsaturated hydrocarbon becomes saturated. Acetylene, for example, has carbon-carbon triple bond. One hydrogen here and one hydrogen here. Each carbon can have only 4 bonds. So a couple of these bonds are broken and more hydrogen are added on either side to become ethane. Similarly, here we have carbon-carbon double bond, but again, if you add hydrogen, it is changed to carbon-carbon single bonds. This is called saturation, for which we require a catalyst like platinum, which has the property of occlusion. When hydrogen reacts with a metallic oxide, reduction takes place to give you pure metal, and water is produced. Heat is required. So here hydrogen is a reducing agent. It's used in metallurgy. Here brown compound is changing to gray residue, yellow compound is changing to gray residue, black compound is changing to pinkish brown residue. And even water vapor is formed, which will turn cobalt chloride paper from blue to pink. These are the observations you have to learn. Mark this as a good reason. Notice that the excess hydrogen is burnt off, because if that excess hydrogen enters the atmosphere, that area can be combustible. Uses of hydrogen to make coal gas, water gas, which is a mixture of two gases. For example, water gas is hydrogen plus carbon monoxide. It's a fuel. To make compounds like HCl and ammonia, in hydrogenation of oil into ghee. Mark this as a definition of hardening of oils. Certain conditions are required for that. To make synthetic petrol, mark it as read. In metallurgy, which I just explained, as a reducing agent. In oxyhydrogen torch, which is used for welding. If you burn oxygen hydrogen in that machine, it can produce 2500 degrees Celsius, enough to weld metals and cut metals by melting them first. Redox reactions. Mark this as a definition. In this equation, hydrogen is a reducing agent, but it itself is undergoing oxidation. Copper oxide is an oxidizing agent. It itself is undergoing reduction. Since both are happening simultaneously, it's a redox reaction. All displacement reactions are redox reactions. Definition of oxidation and reduction. Oxidation is either addition of oxygen, removal of hydrogen, addition of electronegative atom, or even loss of electrons. Reduction is the opposite. It is removal of oxygen, addition of hydrogen, removal of electronegative atom or ion, or gain of electrons. Learn the list of oxidizing and reducing agents. Let's understand one example here. Here in copper oxide, copper's valency is 2+. Its oxidation state is 2+. And oxygen is 2-. It's an ionic bond. Copper is 2+ means it has deficiency of 2 electrons. Then it became copper. Whenever an element is alone, its oxidation state is 0. It's neutral. So from 2+, it became 0, means it gained electrons. And gaining electrons is called reduction. Losing electrons is called oxidation. For example, here in FeCl2, Fe was 2+, means deficiency of 2 electrons. And here Fe is 3+. If you try the crisscross method, Cl is -1, right? So 3+ means deficiency of 3 electrons. So how did it become from 2+ to 3+? Well, it lost an electron further. And losing electron is called oxidation.
Hi students, this is AJ sir. If you found this video useful, press the like button. Also, if you'd like to enroll for my test series or online lectures, email me or message me on Instagram. Check my description for more information.